I wanted to take a quick minute to go over uniform convergence since that seemed to be an issue in the feedback that I got from last week. And thank you for filling that out. There's some other issues, but this was the one that I think bubbled to the surface a little more. Just to remind, and it is confusing. Just to remind you of the issue at hand, we are considering a series of functions, right? Rather than a series of numbers. We're letting u sub n now be u sub n of x, which means that we have an infinite sum from n equals 1 to infinity of u sub n of x, right? So that's just, and this is all from lecture, right? All of these terms up to some u sub n of x. And it's clear then that if we do the sum of u sub n of x over infinity, we get, if it's convergent, an actual sum of the series s of x, and we can also define a partial sum, right, of s sub n. And the idea behind uniform convergence then is that if you consider a region, you might have a function, right, that this series is converging to. And the sort of abstract idea is that given some arbitrarily small distance from that function, right, you can approximate, that is your series of functions can be a pretty good approximation to that ultimate s of x. This is what we see when we take enough terms, say in a Fourier series. And the idea here is that we get uniform convergence for some n bigger than another capital N, as long as this is independent of x. And I think that's the real tripping point here. When we talk about uniform convergence, we're looking at how this converges in the region irrespective of the value of x. So in this little mock-up case that I've got here, what this is saying is that if you take high enough terms, a high enough sum, you can get close enough for whatever you've defined your epsilon to be to what that function actually represents, right? In the case of, say, a step function and you're trying to use Fourier series, you need to use quite a few terms. But you might have, say, like in this case, S1 might look like that, right? So nowhere near convergence. And S2 might look like that. So it's some of it's within that epsilon, but some of it is not, so it's clearly dependent on x, and maybe by the time you get to s sub 10, all of those values at every x is within that tolerance that you've set, right? And so we would say that, and say s sub 10 is that small number, we would say this series is uniformly convergent on the interval a, b for n greater than 10. So that's sort of the abstract idea about it, and where it can be kind of tricky is if you try and find that n. You can. For some series, it's a little easier than others. Practically speaking, if we want to find out if something is convergent, though, we would use the Weierstrass test, right? So I did an example that was kind of straightforward for that. So this is the, I always misspell that. Sorry. This is the Weierstrass test, right, for an infinite series, right? So for u sub n of x, and we know that this is uniformly convergent if there is another series of numbers, m sub I, right? So this is we might even call it a sequence, right? That is convergent on the interval in question. So the interval a, b, right? And everywhere the absolute value of a u sub I of x is less than m sub I. Okay. So this is how we would test uniform convergence. The picture up here is sort of the abstract concept. This is the application. So let's look at how we would use that. I did one example in lecture, but let's look at the problem you had in the homework. That is the sum 1 plus x to the n, right? And you were to show basically where is it uniformly convergent for positive values of x. Right? So, and the convergence part of that is just using a comparison test. So the part A was to find the region in which it's convergent, and then the second part is where is it uniformly convergent. So the one thing that we can do here then is we need to identify our m. Right, so let's let m sub, let's go back to n, be equal to 1 over s to the n, where s is greater than 1. Now if you think about that, right, this condition over here comes from the fact that we know that this is a geometric series and it converges as long as s is greater than 1. As soon as s is equal to 1, right, that's an infinite sum. If it's less than 1, it diverges quickly. But we know that as long as s is any small distance, say epsilon, away from 1, right, then m sub n converges, right? So if m sub n converges, or actually the sum of that converges, then we can compare. That is, we look at our u sub m, 1 plus x to the n, and ask ourselves, when is this less than or equal to that? Right? Because this is our m, and this is our u. Well, the only time this is true is when x is less than, got this backwards here. S is greater than or equal to this number s, right? So if x is greater than or equal to s, and s is greater than 1, then we've met the criteria for uniform convergence. And so the statement then for this sequence, or this series, u sub n of x is equal to getting ahead of myself here. The sum of u sub n of x equals the sum of 1 over 1 plus x sub n is uniformly convergent on x greater than or equal to some number s, which is greater than 1, and essentially x all the way to infinity. Okay? So again, the 2 points here and the takeaways here are the sort of the holistic view of what this means as we converge to a function, and how we determine what those values are. In general, will always be able to do something like this. And your book has another example where it looks at a geometric series as well. Now, I know that a couple of you asked, how do we compute the infinite sums for series? That in itself would be an interesting diversion, and if people are interested in looking at that, I'd be happy to prepare something for that that involves mathematical induction. For the purposes of this class, we're almost always going to run into either the geometric series or infinite series that we can relate to integrals and then evaluate the integrals. So anyway, I hope this was helpful. Again, this was in the homework and a response to your questions. I'm going to give you guys one who haven't filled out the reflections for this week, a couple more hours to please fill that out before I have to give you a 0 on that. This is helping me make this the best class possible. Okay? All right, I'll see you guys tomorrow. You're doing great, and thank you.